All right, so welcome to MathStat 341. It's good to be back in person again. So this is lecture 16. This is a lecture that can go at various points in the semester. In the spring semester, I often do it on Patriots Day when the Boston Marathon is being run. I almost did it this year, a few days ago, when the Boston Marathon was run, because it was actually moved to the fall this year. But I figured it would be better to wait until we were somewhat deep into the baseball playoffs to do a lecture on baseball mathematics. Out of curiosity, how many people here have absolutely no understanding of baseball? Okay, so I'm not going to then have to go through and explain things. This is excellent. And so what I want to do is I want to use baseball as a vehicle to talk about statistics and modeling. And what happens as we start developing the different tools that we have in this class. We're looking at different distributions, we're looking at means and variances and moments. How do you actually use this stuff to do something that people might actually care about? And so I've done a lot of work over the years in sabermetrics. This is the art of applying mathematics and statistics to baseball. You can, of course, apply this to other sports. I am happy to have conversations about this, but not when anything is being recorded. So if you've read Moneyball, I've met a lot of people from there, and there are absolutely stories I can share, but we will have to have an equipment malfunction first before that can happen. All right, so I always like to dedicate this talk to my great uncle, Newt Bromberg, who my son is named after. My daughter's actually named after his wife, who assured me when I was a very little kid and asked, will I live long enough to see the Red Sox win, that yes, I would actually make it. And when the Sox finally won in my lifetime, the first person I called was not my father, was not my brother, but his youngest son, who was the biggest Sox fan in the family, who had bought a bottle of champagne in 1975 when he thought the Sox were finally going to win it. And in disgust after what happened that year, willed it to his grandkids, thinking maybe they would live long enough to see the Red Sox succeed. Anybody familiar with the 1975 World Series? Considered by many to be the greatest World Series of all time, I think the best quote about it is whoever wins Game 7 will have a decided advantage. Just in terms of just how good and how close the series was. All right, so this is just a picture of Fenway Park in the old days. I actually could have gone to Game 3 in Boston if I had been feeling better. My father had gotten sick and he and my mother were in town and had tickets, but then fortunately he rallied, so my son and I didn't have to make the long trip back and forth, but we were willing to do that. All right. How many of you have heard of the Pythagorean one-loss theorem or the one-loss formula? We might have talked a little bit about it when we were doing some things earlier. And so the idea for today is I want to talk about what is the one-loss formula. And if you look at Major League standings, they actually have this under the expanded statistics. And if you think about it, on web pages, it's really bad to have a lot of content because that takes away from ad revenue because you could have more ads. So anything they put up has to be really important. So if they're going to display a statistic, it should be a good statistic. So I want to talk again about the ideas and techniques of mathematical modeling. The exam was open book, and the exam is open book for a reason. As you go further in life, this is the 21st century. You have access to a wealth of information very quickly. You're not going to have to memorize all the different distributions. Now, it helps to know them. It helps not to have to be looking up everything. But I want to really emphasize in this course the powers of mathematical modeling. How do you come up with enough key features to capture what's going on in the system? We'll see how advanced theory enters in very simple problems. How many of you have ever done the drowning swimmer in high school calculus? Someone is drowning in the water and the lifeguard has to get to the swimmer. No one. Oh, okay. So so if you have somebody drowning over here at the start and the lifeguard is somewhere over here away from the shore, what path does the lifeguard take to get to the swimmer? And what path should the lifeguard take? So how do you think most lifeguards, what path do you think they choose to get to the swimmer? Straight line. What they really should do is they should run at an angle because they run faster on land than they swim in water. So you don't run straight underneath, you actually run at some angle. And if you know physics, this is the angle of incidence equals the angle of refraction. This is Snell's law. between two different media where you have two different speeds. It's the same mathematics. And you end up having a quartic that you need to solve from a very simple problem like this. So there's a lot of times where the problem is very easy to state, but the mathematics needed to solve it can be hard. And then what's also very nice in the real world is a lot of times you can say, just screw it, just run in a straight line. It's going to be close enough. And when you consider that there are probably people on the beach, the opportunity to run in the optimal path might not even be there to begin with. We will see how you can have opportunities from inefficiencies. So if you know things that other people don't, you have the ability to make better decisions. And then finally, if anybody is interested, I've already mentioned some problems like this, but there's a lot of opportunities for research. I've done a lot of work with students in the field. I have several who are working at Major League franchises right now. So if this is something that you're interested in, please let me know. All right. So the goal is to find a good statistic to describe the real world. This is a problem we've had many times. If I tell you exactly what to look at, after a while, you guys are all, I don't mean this in a condescending way, I won as well, you're all trained monkeys. We have a bunch of tools at our hand, we know how to apply them to standard problems. So if we're given the problem, we know what to do. The difficulty, the challenge is coming up with what's worth looking at. That's what makes you the highly paid person rather than the trained monkey in the basement. And that's why I really want to emphasize in the lectures, thought processes like this, and leave a little bit more of the standard stuff to the book for you to look at. And again, if you have questions, just email me. If I'm in my office, it's office hours. We'll find a time to chat. But I really want to talk about the mindset for stuff like this. All right. So we've actually done this before, but this is not surprising that this comes up again. I love this problem. This is the Harvard Bridge. I'll just do this fast because we've already done it early in the semester. They were measuring how many smoots it took to get from one end to the other. And that is not a great statistic. All right. We've talked a little bit about this one as well. And so this is from 2018. And I've mentioned that if you go online now, you will not see these numbers because they have retroactively adjusted the numbers and awarded the Yankees a loss. Now, as a Sox fan, I'm always happy to retroactively adjust the numbers and add losses to the Yankees. That's perfectly fine with me, except right now, this really screws up a little bit of my lecture. And the reason is, depending on which statistic we use, you have the ridiculous situation that there's a different team in first. So if you go by winning percentage, well, the Yankees have a slightly better winning percentage than the Sox. But the Sox played 6 more games, winning 4 and losing 2. Almost any time late in the season, it is great to win 4 out of 6 games. But right now, the Sox and the Yankees were playing so well that actually lowered the Red Sox winning percentage. You basically get half a game for a win, you lose half a game for a loss. So the Sox are net 1 game above the Yankees. So you have the ridiculous situation of the Yankees are in first place, 1 game behind the second place Red Sox. Now, to me, this is humorous, but it doesn't really matter because by the end of the season, the statistics will coalesce. So this is just a fluke of when we're looking at things. I don't think I've done this one before. If I tell you your team has won 3 out of the last 4 games, are they doing well? Yeah, what's the winning percentage? 0.75, 75%. What happened 5 games ago? If I tell you they've won 3 out of the last 4, what did they do 5 games ago? They lost. Why? I would have said you've won 4 out of 5. Unless I'm deliberately doing this to hold that in strategic reserve, they almost surely lost 5 games ago. What did they do in their last 3 games? Did they win their last 3 games? Yeah, they've won 3 out of their last 4. Did they win their last 3 games? No. Why not? I would have said they've won their last 3 games. So if you look at their last 3 games, they're 2-1. If you look at their last 5 games, they're 3-2. And if you look just right at 4 games ago, they're 3-1. So by looking at just the right moment in time, I can really influence how you look at something. And so you always want to be careful about how you can mislead with statistics. Right. So this is, I think, the first team where I was the head coach. The goal is to go from something like this And if you ever find yourself coaching T-ball, there is a support group. Just email me and I can pass on what I have learned. Out of curiosity, if any of you can detect which shirt is not actually green and has been digitally altered, that's extra credit. One of the shirts is not green and has been digitally altered. To go to something like this, to go to something like this with championship rings, or actually I guess medals, and then eventually to go all the way up to a World Series ring. So this is a Red Sox World Series ring. I was visiting, related to my father's cousin. I was visiting his sister, and we were going out for a walk, and we ran into one of their neighbors, and we were just chatting about the Sox game the night before. And he just casually said, he remembers the first time the Red Sox gave him a ring. And unless you're a mathematician, most normal people would never say first unless there's also more. So he actually worked security for the Red Sox in Florida, and they were so generous, he ended up with a multiple World Series rings. I won't say what I offered in exchange for that ring, but he was not up for the trade. All right, so here are the parameters we're going to need for what we're doing today. So RS observed is the average number of runs scored per game. RA observed is the average number of runs allowed per game. And then gamma is just some constant that's going to be different for each sport. So I'm going to do this for baseball. You could, of course, do this for other sports. Other sports, it's a little bit harder because you don't have as much data. Baseball has 162 games per season. What sport of the ones that really matter in America do you think is going to be the hardest to do something like this, to predict a team's winning percentage? Football. So there's many reasons why. What's one reason?
Fewer games.
Fewer games. And in fact, in football, you often have established your seeding with 1 or 2 games left to go in the season, at which point some teams decide to just rest their players and be very protective. And so if you are not playing your hardest for 1 or 2 games, oh my God, that's 1/16 or 1/8 of the season of data that you have to throw away. And so what Bill James numerically observed, and he is the god of the subject, is that a really good estimate of a team's winning percentage, the number of wins over the number of games, is approximately runs scored to the gamma over runs scored to the gamma plus runs allowed to the gamma. And he found taking gamma equals 2 does a really good job. Why do you think he called this the Pythagorean one-loss formula? Yes. But why the word Pythagorean? What do you think of when you hear Pythagorean or Pythagoras? Triangles. A squared plus B squared equals C squared. You have a sum of squares in the denominator. Except for the triangle in the outfield of Fenway, you really don't have triangles in baseball, right? This has nothing to do with the geometry of Pythagoras. It has to do with sums of squares. When he was doing this, you don't have the personal computers that everybody has. You have little dinky calculators. So you take something very simple like 2, because it's easy to work with. Is there anybody here who's over 21? Okay, so I've talked to, I know some people here about this. When you are over 21, you suddenly learn how to drink, and you suddenly learn that there are such things as mixed drinks. And so when I'm going to be very careful how I do this because this is being recorded. When I was in graduate school, I found myself one day as a bartender, and the only drink I knew how to make was a White Russian, which is very easy. One way to do is 2 parts milk, 1 part vodka, 1 part Kahlua. Who thinks that this is the optimal mix for a White Russian? Okay, why do you think they make it, with the 2-1-1 ratio?
Because it's the least expensive part.
Well, if you want to do that, bump up the milk. But why don't we have, yes. It's easy, you have, and again, when you turn 21, you actually see mixed drinks being made, you might have, a better chance to answer this. So it's really good that people aren't floating out answers. If ever there was a day to show up to class drunk, all right, you have little spigots attached, you can go, boom, and it gives you 1 shot, 1 unit. And so if you do nice integer numbers, it's very fast as a bartender. And if you have a lot of drinks to do, it's very, very good. But it's almost surely not the best way to do it. If you look in baseball, if you know statistics like, on base percentage or on base plus slugging. We're doing exact integer multiples of things. And in the 21st century, now that we can do everything by computers, I'm not convinced that this is the best way to do it. It's treating everything too equally. So you want to really think about the weights you're using and the different choices you're making. And so over here, the fact that we're using gamma equals 2, well, when you're doing everything on a calculator, squaring things is actually pretty easy, as opposed to trying to calculate things to the 1.8 second power or whatever. And so nowadays, the best fit value of gamma is a little bit lower than 2. A lot of it is going to depend on the error that you're looking at. There's the dead ball error in baseball where there weren't that many home runs hit. And there's what is politely called the steroid error, where people were ingesting certain substances, which greatly increased the ability to hit home runs, which greatly increased scoring. So there can be fluctuations. All right. So just as an example, in 2009, the Sox were 95 and 67, scored 872 runs, allowed 736 for prediction of 93.4 wins. And the Yankees came in at 103 and 59, but were predicted to be around 95 wins. And so one of the things you always want to get a sense of is, well, how accurate is the formula? And what do deviations mean? I will skip the 2011. So, why do we care about something like this? So here are 3 reasons. The first is extrapolation. So you can use this to try to get a sense of how things are going partway through the season, and then determine whether or not this is a season where you have a chance of making a significant run deep into the playoffs, or if this should be a rebuilding year. And if it is a rebuilding year, then maybe you don't trade some people to just get that hired gun who can help you towards the end of the season. And so I remember a couple of years ago, the Yankees started off 21 and 29. It was a wonderful start to the season, but all the metrics said the Yankees were a victim of bad luck, and that they had a fundamentally good team, and they made a move to get another top starter and made the playoffs. Another reason we like statistics like this is it helps us evaluate managers. So if you're consistently overperforming, this might mean you have a better way to use your bullpen or your players, and you're able to get more production out of them. Remember, it doesn't really matter if you lose a game by 1 run or by 20 runs. Now, it could make a little bit of a difference in terms of then how you're prepared for the next game. Have you burned some pitches or whatnot? But at the end of the day, if you're just counting wins and losses, it doesn't really matter how many wins you have by 1 run, by 2 runs, by 5 runs. In other sports like soccer, when they come down to tiebreakers where they could look at goals for and goals against, that's a little bit different. But in baseball, what we're doing here right now, if you're consistently overperforming, this is a good indication that your manager is actually doing a good job. And Joe Torre for the Yankees actually consistently overperformed what you would expect. And then one last thing about the statistic that I really like is that it's easy to use. You give me how many runs scored, allowed, and gamma, and I can give you a prediction of the winning percentage. So if I want to figure out how much money is it worth signing somebody, well, let me see if they're a pitcher, how many fewer runs do I expect to allow in a season? If they're a hitter, how many more runs do I expect them to generate either through batting or maybe batting and fielding? And this can give you some sense of how much it's worth to hire them. So if you are right on the cusp of making the playoffs, somebody who can get you a few more wins is going to be worth a fortune to you because of the value of going to the playoffs, the postseason revenue, and of course, just the pride of actually winning. So if I told a team like the Red Sox, or let's not do the Red Sox, let's do the Blue Jays this year, who just missed out on the playoffs with 90 wins on the last day of the season. If I could tell the Blue Jays, I'll give you a guy that will generate 6 more wins for you next year, how much is that worth? That would have leapfrogged them over the Yankees and the Red Sox. It would be worth a lot. How much do you think that would be worth to the Blue Jays? And you need a little bit of baseball knowledge now, versus going to the Orioles and say, I've got somebody who will give you 20 more wins. Yeah, the Orioles had over 100 losses last year. They had on the order of 50 wins. So they were so far away from the playoffs. They were so far away even from an average season that you give them 20 wins and they're still not an average team. So Yes, it'd be great not to suck as badly as they did, but in terms of what is it worth it to them, it's not going to be enough for them to make it to the playoffs. Whereas that 6 more wins for the Blue Jays would be incredibly valuable. So when you're trying to figure out the worth of someone, it's not an absolute question. It's what are they worth with the rest of the pieces you have? And so sometimes if you're really close, that little push across can be worth a tremendous amount. I will risk saying this, on the political side, if you come out too early in favor of something, well, then you can't really get that much for your vote. But if you have, I don't know, something that you need every single vote for, and some people hold out, and this has happened numerous times in a nation's history, then the longer you hold out, the more you can command for that one vote. And it's the difference between getting something and not getting something. So when you're trying to assess what something is worth, value is relative in many situations. All right, we go now just to some basic probability. And so our goal is to come up with a way to model a scoring distribution. So imagine this is a histogram of how many games we score: 0 runs, 1 run, 2 runs, and so on and so on. Can we come up with a probability distribution that models this? So we've hopefully seen this a couple of times before. So if X is a random variable with density P, if it's continuous, that means P is non-negative, it integrates to 1, and the probability we take on a value between A and B is just the area under the curve from A to B. And this is why we care so much about integration. Integration allows us to compute probabilities. This is why you're supposed to have already taken 3 calculus classes before you're even allowed in here. The mean, or the expected values, is the integral of xp of x. We've talked about this a lot. And then the standard deviation is a measurement of how spread out things are: x minus mu squared p of x dx. So these are all the standard statistics. And an independence would be knowledge of one random variable gives no knowledge of the other. After the last 2 losses, I have decided it is time to put on the lucky shirt. All right, we will see if they're independent. So if the Red Sox always win when I put on my lucky shirt, is it possible to determine if the events are independent after the Sox and the Astros play today? So imagine the Sox always win when I wear my lucky shirt and I'm wearing the lucky shirt. Will we be able to tell later today if the shirt truly is lucky? Can we tell if the shirt is not always lucky? Hopefully not. Hopefully we will not have that data point. But in the unlikely scenario that the Red Sox lose, then you would be able to determine that the shirt is not always lucky. If the Sox win, however, is that proof that the shirt had anything to do with? No. All right. Anybody ever watch the old Charlie Brown baseball? Oh, so I've seen a couple. I saw at least 2 people nod their heads yes. This is, I think, a record for me. That somebody's actually seen it. There's a reason he has a sad expression. Games never go well for Charlie Brown and his team. And so the reason I'm having him as my picture here is here are the 2 guidelines for modeling. The model should capture the key features of the system, and it should be mathematically tractable. What do you think the problem is with those 2 points? So I want to capture the key features of the system, and at the same time, I want to be able to solve it. Yes, real systems have a lot of features. And the more features you put in, the harder it's going to be to come up with a nice closed form solution. So these are actually pulling you in opposite directions. So one of my favorite examples, I may have used this before, is Galileo dropping the 2 spheres off the tower to show that the mass doesn't matter in terms of determining how long it takes to fall. So how many of you have heard of that physics experiment? Extremely famous. It drops 2 spheres and they land at the same time to indicate that the mass of the sphere does not really play a role, or if it does, it plays a very, very small role in the time to drop. Okay. Does anybody remember what the colors were of the 2 spheres? Why not? You're saying it doesn't matter? So one thing is you would hope that they would both be the same color, so that color wouldn't matter. I can come up with a situation where color might matter. Maybe one color absorbs heat better than the other. Maybe you leave it outside for 8 hours, so one sphere is hotter than the other. And now when you drop, and this is the danger, is that it's not the color that matters, but the color is a proxy for something else, to the temperature change. Shortly after my son was born, I read a very, very scary study that said that children who watch too much TV and video when they are young are more likely to become autistic. And so what do you think my first response is as a new father? Be very careful about the videos. What do you think my second response is as a new father who has a degree in mathematics? Question the study. So the study said that the more TV you watch, the more likely you are to become autistic. So can somebody tell me what data you think the study should have? Well, if your premise is the more TV you watch, the more likely you are to be autistic, what data would you like to see in the study? Okay, so you want to see how much TV are they watching and what happens to them later in life. Okay, what are you planning on majoring in, if I may ask? Okay, good. So it's really good that you're not majoring in any of the fields of these authors, because you clearly do not understand how to do studies. Because they, but again, you haven't gone to grad school. You haven't spent years studying this, so you don't know what data to collect. See, they collected precipitation. Because if it's raining or snowing, then you're more likely to be indoors. And if you're indoors, you're more likely to be watching TV. At which point then we went back to watching Muppets on YouTube. And so it's hard to collect data of how much time people spent watching TV. And so sometimes when you have something that's hard to collect, is there something related to it that's easy to collect that I can gather and then try to make my estimates from that? Well, there's a lot of questions I have. Are you looking at average precipitation? What if I have a few days that are extremely big weather events? That could really change the average, but not change the number of days I'm indoors by a lot. What if it's raining late at night? There's so many possible concerns with this. All right. So here's one possible model. Runs scored and runs allowed are independent random variables, and they're drawn from some nice densities. Can anybody think why runs scored and runs allowed might not be independent? Yes. Okay, but why is there a dependence between runs scored and runs allowed? So maybe you just have your own scoring distribution and your own, and you just might have a bad total for each. But how does having, say, giving up a lot of runs in the game, how might that affect your ability to score a lot of runs? So one is you could be demoralized. What else? Let's say you're up by a huge amount and there's one inning to go. What might you do if you're up by a huge amount? You might relax. You might put in people you normally wouldn't. I remember once for the Red Sox, I think it was Rumlinger came in to pitch the ninth, leading 10-3. So all he needed to do was get 3 outs for the Sox to win. They couldn't list his ERA, how many runs he allowed on average per 9 innings, because even though he had pitched for the Sox for a while, he had yet to record an out. So this was a division by 0 problem, and his ERA was effectively plus infinity. I believe he proceeded to give up a grand slam. He did eventually get the 3 outs, but he would not have been brought in a close situation. So if you have a large lead, if you've scored a lot of runs, you might put in weaker pitchers. Or you might, if you have a large lead, you might take out some of your starters, give them some rest, and put in some other people. So there are dependencies. We hope that these dependencies are minor. And if we want to try to calculate the probability you win, we can do it as an integral or we can do it as a sum. So if we do it as a sum, we look at all pairs I and j, where I is greater than j. And so that means this is the probability I score I runs, multiplied by the probability I allow j runs, and I just do that sum. Or I can do the calculus problem. Technically, I should integrate over y strictly less than x, but because this is a continuous function, you're going to strictly less than x, or x makes no difference. So which do you think is a better model for a sport like baseball? Continuous or discrete? Discrete. I would love to see a headline, Sox beat Yankees pi to E, right? For so many reasons. It's never going to happen. We will do the continuous one because it is easier to work with. We have a lot of theorems about integrals. We have a lot of abilities to get closed form expressions. We just don't have that in the discrete setting. All right, so there's a lot of problems with the model. We've already mentioned a few. One, of course, is can we actually find choices of f and g that do a good job modeling the data? Can we do the resulting integrals and sums? And just how bad are the dependencies? So the first question is, can somebody give me a really good, simple choice for f? What kind of distribution, what kind of random variable would you start with as your simplest case? Simplest random variable you can think of. Yeah, it's just like a uniform distribution. So here's a uniform distribution in 0, 10. It's nice, it's easy to work with, but it has absolutely no bearing on reality. So can somebody give me another possible distribution you might try? Normal distribution, good. And this is not a planted question, it's the next natural thing to try. What's the problem with using a normal distribution like this to model a baseball game? Yeah. I'm sorry? Yes, no matter how bad you are, and we have some examples of really bad teams, you're not going to score a negative number of runs. You also have a positive probability of scoring 1 trillion runs in a game. Now, the probability is so small, it is more likely that I will win the lottery 5 consecutive times while it's singing I Love the New York Yankees, but it is still possible. Well, given that the probability is so small, I'm actually quite happy to take something like this, because I would much rather work with continuous random variable and just go all the way up to infinity than deal with some finite cuts. Can anybody give me another distribution that we could use that doesn't have this problem of negative numbers getting a probability? Yes. Right, so binomial converges too. So can somebody give me like a one-sided probability distribution? I'm sorry? So the more distributions you know, the more modeling you can do. Poisson would work. Poisson is one-sided. Poisson is discrete, but exponential is another natural one to try. The problem with the exponential is the most likely event is a low-scoring game. So this might be better for soccer. What we're going to do is we're going to look at the 3-parameter Weibull. And so the Weibull is basically some normalization constant, x minus beta over alpha to the gamma minus 1, e to the negative x minus beta over alpha to the gamma. So the 3 parameters, alpha is scale, beta is origin, gamma is shape. So first, the beta is the easiest one to understand. It just shifts the distribution left or right by beta units. So it just translates things. If you're modeling a basketball game, no basketball team in the pros is going to score less than 40 points in a game. So you wouldn't be having your probability distribution start at 0. You might have it start a little bit later. The next is alpha. Alpha just rescales things. If you look at it, I've always got x minus beta divided by alpha. So it's just changing the scale of the x-axis. So alpha doesn't really affect the shape of the distribution. Gamma, that's the one that really matters. That controls the shape of the distribution. And so over here, I've shown you a few different choices. If I take 1, 0, 1, I actually get the exponential. For other choices, you notice we have things that basically go up and then come down. So these are, one bump distributions. And it turns out that there's a lot of distributions like this. If you've seen, gamma distributions, you'll see stuff like this as well. And you can model a lot of things like this. It turns out this is a very good distribution to work with, because if you do a change of variables, if you let u equal x minus beta over alpha to the gamma, then you essentially just change this to e to the minus u du. So with a simple change of variables, you have exponential integrals to do. We can do exponential integrals. All right, so they have a lot of different applications. In situations when gamma is less than 1, this models things with high infant mortality. gamma greater than 1 models things that survive for a long time before they decay. All right, so again, the more distributions you know, the better. I came across this when I was doing my analysis because of some experience I had in nuclear physics and random matrix theory, some experience I had in classical statistical mechanics of just some distributions that were worth doing. And I tried some very simple cases. And I first tried the exponential, then I tried the case when gamma equals 2, not realizing at first that it was the Weibull family. And I said, what do these distributions have in common? Oh, it's something of the form, x to the, n minus 1, e to the negative x to the n. And then I did some web searching and I found the Weibulls. So we've seen the gamma function, I think, a few times. Gamma of s is the integral of e to the minus u, u to the s minus 1. It generalizes the factorial function. We'll do a lot more with this later. Gamma of n is just n minus 1 factorial. And a nice calculation, and this is just a Calc 2 problem, is to show that the mean is just alpha gamma of 1 plus 1 over gamma plus beta. And similarly, we can have an expression for the variance. So what's nice is we have a closed form answer. So for instance, if we have to, and we'll do simulations, but it's much nicer if I can tell you, here is how things depend on a parameter. And if I increase my runs by 1.2 on average per game, which is a huge increase, how much is that worth to me? It's nice to have formulas that clearly depend on the things of interest. And so we can calculate the mean and the variance very easily for the Weibull. And again, all of this is in the slides. And then I have written multiple papers of this with students. And so all the calculations are in great detail there as well. So to just calculate the mean, here's how you would do the calculation. I just have x times my distribution. Well, I'm going to just change variables. Before I change variables, I write x as x minus beta plus beta over alpha. And now that just gives me another x minus beta over alpha because everything's occurring like that. And then the beta, well, beta times the probability distribution just integrates to beta. And this shows you, as you would expect, that all beta does is just shift everything. And so now if you change variables, you get e to the 1 over gamma e to the minus u du. And then, oh, well, if I just play around a little bit, I can write it in the exact same form as a gamma distribution. And then I can just say, oh, it's a special value of the gamma function. So the whole point here is that we can actually do these calculations without too much trouble. All right, so the Pythagorean theorem. So here is a snapshot from one of the major websites. And they give you statistics like wins, losses, winning percentage. You technically don't need the winning percentage because if you have the wins and the losses, you can just calculate this. But it's risky to trust Americans with division like this. There are stories of people who are upset that they're being cheated because they only got 1/6 of something and somebody got 1/8. How come I didn't get 1/8? You can't make this up. And so it's better to just put a little bit extra stuff at times. But one of the things they list is the XWL. And the XWL is the expected one loss. This is the Pythagorean predictions. And you can see how good of a job it does against the actual values. I'm going to skip the log5 method. We had talked about this earlier in the semester. And so, okay. This way, at least you can always hit the pause and the dip. All right, so here is the Pythagorean formula. My interest in this was inspired by a question one of my students asked years ago at Brown. If we assume that the runs scored and runs allowed are independent random variables drawn from Weibulls with the same gamma, then the winning percentage is essentially run scored minus beta to the gamma over scored plus to the gamma plus allowed to the gamma. And so we take beta equals -1/2. And the reason is the only ones that can actually be scored are 0, 1, 2, 3. You don't want to have your bins structured so that the action is happening right on the boundary of 2 bins. So if I have beta equals -1/2 and I shift, the first bin, or the 0th bin if you want, goes from -1/2 to 1/2. The center 0, great. The next bin is from 1/2 to 3/2. The center is 1. So it's very natural to choose beta to be -1/2. So we want to calculate the probability that one team beats another. And so if I tell you what the means are, I can actually figure out what I should choose for my parameters alpha. And I just choose these parameters as a function of beta, which is going to be -1/2, and then gamma, which we'll determine later, so that I have so that my Weibulls have the correct mean. And I want to calculate the probability that x is greater than y. And so I have the integral x goes from beta to infinity, y goes from beta to infinity. And so the first thing is, let me look at the y integral. I might as well just change things and shift things by beta. And so the y integral goes from 0 to x. Well, I can go from 0 to infinity and I get 1. And then I subtract the integral from x to infinity. So I have something like this. Well, when I look at the integral like this, the x integral times 1, well, that just integrates to 1. So that's easy. And then the other part is I'm going to have an integral of x, and I'm having two different exponents. They each have an e to the negative x to the gamma, but they're divided by different things. And so if you choose alpha, and it's a little bit annoying that it seems to be cutting off at the very bottom, I apologize for that. You get 1 over alpha to the gamma is 1 over alpha rs to the gamma plus 1 over alpha ra to the gamma. Has anybody seen anything like that before in another class? That the way you combine two objects is the reciprocal of the combination is the sum of the reciprocals. There's two, yes.
That's the resistors.
Resistors. I always forget if it's resistors in series or parallel. I think it's resistors in parallel. And the other is in physics in center of mass problems. So this idea of combining things like this is something that we see many, many times. And so what I can do is I can just play a game like this and I can say, oh, well, if I just let alpha be this combination, I now have something that looks a lot like a new Weibull. It looks like a Weibull with parameter alpha rather than alpha rs or alpha ra. Well, I've got the wrong thing down here. I don't want to have these. I want to have just alphas. Well, that's just multiplicative paperwork. So multiplicative bookkeeping, I just put everything in. And when the dust settles, I end up with a nice expression for what the integral is. I then substitute in terms of the means, and I get the expression that I want. And so it's completely missing the bottom line. This is fascinating. So the RS minus beta is estimating the average number of runs scored per game, and the RA minus beta, the average number of runs allowed per game. So this shows you that the Pythagorean theorem follows from these assumptions. Whether or not these assumptions are reasonable is another question. You can do some work, and we'll talk a little bit about that now. So I'm going to choose a season entirely with purpose. I will choose the 2004 season. And so here is the distribution of runs scored and runs allowed for the Boston Red Sox, who won the World Series. So I will list them first. Does it look like the data is doing a good job being described by my proposed best fit Weibulls? Yeah, but as students in a math stat class, we want to do better than it looks good. So we want to develop some tools and techniques. How many of you have seen chi-squared tests? Okay, so a lot of you have seen chi-squared tests. And so we will talk a little bit about those now and a little bit later in the semester. We want to have a way to quantify how good we're doing. So we can look at all the different teams. And what we're going to do is we're going to look for each bin. We're going to see how many times we observe that number of runs. And we're going to subtract off how many times we predicted to have that many and square it. And do the same thing for runs allowed. And the smaller this sum is, the better fit we have. And then the real math stat content is quantifying, if the value is a certain level or smaller, it's very likely that you're doing a good job modeling. If it's a certain value or higher, it's very likely you're not doing a good job. But you can calculate these values and you can see how they look for different teams. So here's the Red Sox. Here's the Yankees. Again, looks reasonable. Here's the Baltimore Orioles. Little concern on the runs scored. The runs allowed seems to be a little bit more consistent. The next one is the Tampa Bay Devil Rays. They may not have had a great season, but at least they know how to exponentially decay. Wonderful. What about the Blue Jays? But they're Canadian. Remember the metric system? No, this has nothing to do with the metric system. It's actually good that the Blue Jays are a little bit off. And the reason is some advanced theory. So we've got a few minutes left. So I think everybody agrees that if we flip a fair coin 1,000,000 times, or better yet, simulate flipping a fair coin 1,000,000 times, we expect about 500,000 heads. Would you be surprised if you got 512,216 heads? You're off by about 12,000. What if you're off by 32,000? So the question is, what's reasonable? And so later in the semester, we're going to do the central limit theorem. It turns out you should be within about 1,000. That for a lot of things, the right growth rate is the square root. And the square root of 1,000,000 is 1,000. So we expect to be within 1,000. So even being off by 12,000, I would be very skeptical. So it's a good exercise tonight. Just go home. I'm not giving you that much homework. Write a computer program. Have your computer flip 1,000,000 times and just see. So consider n independent experiments of flipping a fair coin 1,000,000 times. What's the probability that at least once we're outside this window? Well, if we do it 5 times, there's a 22% chance that at least 1 out of the 5 is not in that band. If we do it 14 times, and back then, one of the leagues had 14 teams, one of the leagues had 16 teams, then we would have it about 51% of the time. If you have 50 teams, if you do this 50 times, it's about a 92% chance. And it makes sense, as you get, this should happen 95% of the time you should be there. By the time you're doing it 95 times, you're almost certain that it's going to be outside at least once. So you can look at the chi-squared values, and we'll talk later about degrees of freedom and whatnot, but essentially 95% of the time, you should have 31.41 or smaller if it's doing a good job for the runs scored and runs allowed. And as an independence test, the values, they should be about 134.4. And if you look, the only one that's a little bit off is the Blue Jays, 41.18. And there's something called the Bonferroni Adjustment. How many of you have heard of the Bonferroni Adjustment? Okay, good. So I'm at least adding some content to the stats people here. So look up the Bonferroni Adjustment. What this basically says is, well, look, if you keep doing a lot of comparisons, your theory could be correct, but you're going to finally get that random fluctuation. I mean, if you do this 100 times, you would expect 5 times to be outside that band. So that means you get to increase the confidence intervals a little bit when you're doing multiple independent comparisons. And when you do that, the Blue Jays, they're 41.18, it's 41.14. All right, the last thing I wanted to just talk about is how many of you have heard of structural zeros? So when you're doing these comparisons, if you take someone to the hospital, hopefully the worst possible outcome is that they just don't get anything improved or fixed. They don't get better. Hopefully you don't make someone worse. Now, occasionally we do remove the wrong organ or whatnot. That is sadly happening, but most of the time, it shouldn't make you worse. So when you're trying to do comparisons, you have to sometimes adjust a little bit of what you compare because certain things are not attainable. When we look at the independence of run scored and run allowed, what must be true at the end of a baseball game? I'm sorry, they shouldn't be equal. So a couple of years ago, the Commissioner of Baseball, and again, the class is almost over, I don't have time to go into details, declared it would be a catastrophe of world order if a baseball game ended in a tie. And this will never be allowed anymore. I don't have time to explain. If you want, I'm happy to talk afterwards as to why this is one of the greatest problems facing society today. We cannot have a baseball game end in a tie. So if I tell you that the Boston Red Sox are playing the Orioles and the Orioles scored 5 runs, what do you know about the Red Sox? They didn't. And in fact, I'm thinking of the Mother's Day Miracle game where the Sox were down 5-0 at Fenway, and in the bottom of the 9th scored 6 runs, the final 2 coming on a 2-out, 2-run error by the Orioles. And so you know that you can't have certain comparisons. And so you have to take into account more advanced theory. And in fact, this is what got me on the radar screen of the sabermetric community, is someone actually noticed this and reached out to me and wanted to talk about this. And because of that, I ended up starting to talk to a lot of people. So just very briefly, if you go through, we get a best fit value of gamma is about 1.74, standard deviation 0.06, median 1.76, very close to numerically observed best fit value of 1.82. You're typically accurate within about 4 games. The Weibulls seem to do a good fit. They seem to behave as if they're independent. Again, we're getting really good results. You can do more advanced stuff. You could try to do a microanalysis. You could take into account ballpark effects and whatnot. You could take into account that maybe after the 7th inning, you have a big lead. So, again, if anybody's interested in stuff like this, I'm happy to talk about various things. The last few slides you've already seen before. You know that he ended up as the chairman of the International Organization of Standards. All right, so this is a good place to stop.